morning one and all. I welcome all the MPCS second year students to the online classes. The summary of last lecture that we have discussed about modes of vibrations in a stretched string. So, I have derived expression for frequency of a vibrating string as nu n is equal to 1 by 2L under root of T by small m. This is the expression for frequency of a vibrating string. So, from this expression we can find out the different modes of vibrations in a string. See, when string vibrates with single loop, when the given string vibrates with single loop, single segment or loop. If the string is vibrating with a single loop, the diagram looks like this. This is the string which is fixed between the two rigid supports. The length of the string be, this is the length of the string, it is fixed between these two rigid supports. If it is plucked perpendicular to its length, what happens? So, definitely transverse wave will be produced. According to our side heading, the string is vibrating with single segment. When string vibrates with single segment, how do we calculate the frequency of the strings, right? See, this is one crest. The distance between this is node, this is antinode, right? This is a node. The distance between the successive nodes is equal to lambda by 2. The distance between the successive nodes is equal to lambda by 2. Clear? So, this is the string which is vibrating with a single segment. So, n is equal to 1. When n is equal to 1, since n is equal to 1, single loop, that is n equal to 1. So, nu becomes nu 1, which equal to 1 by 2L under root of T by m. This is the expression for frequency of the string who is vibrating with a single loop. This frequency is known as what? Fundamental frequency. Fundamental frequency, or there is another name for this frequency, that is first harmonic. First harmonic. This is about the frequency of the wire who is vibrating with single segment or single loop. Let us imagine this string is vibrating with two loops. When string vibrates with two loops or two segments, then how do we calculate the frequency of the string? Right. The diagram for this case is the same length. Here I am considering the length of the string be L only, right. If it is vibrated, imagine this string is vibrating with the two loops like this. Clear? Right. So, when string vibrating with two loops, so how do we calculate frequency of the wire? See, n is equal to 2. Here in this case, n is equal to 2. 2 loops means n is equal to 2. When n is equal to 2, this general expression becomes nu 2. Actually, in the previous lecture, I got the expression for frequency of the wire as n by 2L. As n equal to 1, so this numerator becomes 1. Coming to this case, when string is vibrating with two loops, that is nu 2, n is equal to 2 is equal to 2 by 2L under root of T by small m. This is the expression for frequency of the string who is vibrating with 2 loops. This also can be written as nu2 is equal to 2 into this 2 into, if I take 2 as common, so 2 of 1 by 2L under root of T by m. If I take 2 as common, 1 by 2L under root of 2 into 1 by 2L under root of T by m can be written as nu 1 only. So, this also can be written as 2 into nu 1. So, this frequency nu 2 is known as what? This nu 2 is known as second harmonic. The frequency of the wire who is vibrating with 2 loops is known as second harmonic. There is another name for this frequency, that is first overtone. This is about the 2 loops. When string vibrating with 3 loops, the string is vibrating with 3 loops, when string vibrates with 3 loops or 3 segments, in such case what is the expression for frequency of the wire? Clear? Right. So, this is the string which is vibrating with 1, 2, 3 loops. 1, 2, 3 loops. Clear? Therefore, n is equal to 3. When n is equal to 3, nu n becomes nu 3. This just general expression becomes nu 3, which equal to 3 by 2L under root of T by small m. Clear? This also can be written as nu 3 in terms of nu 1. If 3 into nu 1. This frequency is known as what? Third harmonic. Nu 3 is known as third harmonic or second overtone. In this way, we can derive different frequencies for a vibrating string. The basic expression for frequency of the vibrating string is nu n is equal to n by 2L under root of T by m. Clear? What is T? That is the tension of the wire. What is L? Length of the wire. What is m? Linear mass density of the wire. Clear? Right. So, let us consider the relationship between the nu 1, nu 2, nu 3 and so on. Nu 1 is to, nu 2 is to, nu 3 is to and so on is equal to. What is nu 1 value? Nu 1 only. Already I have expressed this second harmonic as 2 into nu 1, third harmonic as 3 into nu 1 and so on. If I cancel nu 1, finally we get nu 1 is to, nu 2 is to, nu 3 is to and so on is equal to 1 is to, 2 is to, 3 is to and so on. So, this is the relationship between the frequencies in the wire. Clear? So, very important long question. So, previous lecture and this lecture together is a long question. In the examination, they will ask like this, derive expressions for modes of vibrations in a string and explain the different frequencies in the string. If they ask like that, you have to derive the general expression for frequency of the string as n by 2L under root of T by m, that is a previous lecture, and you have to derive first harmonic, expression for first harmonic, second harmonic, third harmonic, and finally you have to write the relationship between these harmonics. From second harmonics onward, from second harmonic onwards, overtones will start. Second harmonic are also known as what? First overtone. Third harmonic or second overtone. Fourth harmonic, next harmonic. Fourth harmonic or third overtone. Clear? Right. And one more thing, remember, we will do some problems based on this formula also. Anyhow, this formula is very important for problem oriented, for long question oriented. Clear? Right. Next topic, that is about laws of transverse laws in vibrating strings. Short question, very important. Transverse laws in vibrating string or transverse laws of vibrating string. Very important topic, but for 4 marks. Short question. Sometimes this transverse laws topic also attached with a long question, that is modes of vibration question. Clear? Right. So next topic is transverse laws in vibrating string. See the relationship between the fundamental frequency, length of the vibrating wire, tension of the wire, and linear mass density can be expressed as 3 laws known as what? Transverse laws in the string. See, first law. All the 3 laws can be explained with the help of the expression for fundamental frequency. What is the expression for fundamental frequency? Just now only I have written. When n is equal to 1, this expression becomes 1 by 2L under root of T by small m. What is T? Tension in the wire or in the string. This is not mass of the wire. This is linear mass of the wire. Linear density or linear mass density. Linear mass of the wire. Or this is also known as linear mass density. What is L? The string who is vibrating with a length which is equal to how much? Small l. So vibrating length. Simply this is vibrating length of the wire. This is tension of the wire or tension of the string. This is vibrating length of the wire. Clear? This is linear mass of the wire. Is that clear? So we are having 3 laws in the string known as what? Transverse laws. The first law can be explained like this. The frequency of the wire, when the frequency of the wire, the fundamental frequency of the wire is inversely proportional to length of the wire, is inversely proportional to length of the wire when tension and linear mass density are constants, known as what? First transverse law. To verify first transverse law, we have to keep tension of the wire and linear mass density of the wire as constant. Simply by changing frequency, you can calculate the corresponding vibrating length. So finally we can verify the relationship between the frequency of the wire and the length of the wire. So instead of nu 1, as in general I am representing as nu only. The fundamental frequency of the wire is always inversely proportional to the vibrating length of the wire when tension and linear mass densities are constant, known as first transverse law. This also can be written as after cross multiplication we get a nu L if I keep one constant here, so nu L is equal to constant, both are same. From this relation only here I am writing as nu into L. If I take just to calculate this nu L is equal to constant, there is one more step, nu is equal. Instead of proportional, if I consider is equal, immediately we have to consider one constant by L. So after cross multiplication, nu into L is equal to constant, K for constant. So this is known as what? First transverse law in the string. Define what is first transverse law. The first transverse law is stated like this: the fundamental frequency of the wire is inversely proportional to the length of the wire when tension and linear mass densities are constants. The second law, second transverse law. This is also known as what? Second law. How do we define second law? The frequency of the wire is directly proportional to square root of tension of the wire, keeping length and linear mass density of the wire as constant. This is the relationship between the frequency and tension. First law is relationship between the frequency and length. This is about frequency and length. Coming to second law, the frequency of the wire is directly proportional to the square root of tension of the wire, keeping the remaining term as constant, that is L and linear mass density as constants. Throughout the experiment, we have to keep length and linear mass density of wire as constant. Simply by changing weights or by changing frequency, you can change the tension of the wire. This is about the second law. Clear? This also can be written as nu by root T is equal to constant. Right. This is second transverse law. Coming to the last law in the vibrating string, that is the relationship between the frequency of the wire and linear mass density of the wire. What is the relationship between the frequency and linear mass density of the wire? That is, frequency of the wire is inversely proportional to square root of linear mass density of the wire. Simply, this is the relationship between the frequency and linear mass density. Frequency of the wire is inversely proportional to square root of linear mass density of the wire, keeping length and tension of the wire as constants. Is that clear? Known as third transverse law in the string. This also can be written as after cross multiplication we get nu into root m is equal to constant. All the three laws together are known as what? Transverse laws in vibrating strings. And remember, this is the very important question for 4 marks, short question. Nowadays, short question is carrying 10 marks. In COVID pattern, short question is carrying 10 marks. So, you can expect this as 10 marks question. In the examination, they will ask derive or explain about transverse laws in stretched string. If they ask like that, you have to write the statement and expression. Statement and expression. Every time you have to write, you have to state the law, and after that you have to write the corresponding expression, so that you will get the full marks. Sometimes they will ask what are transverse laws in the stretched string and explain the modes of vibrations in a stretched string. This question may attaches with long question also, right? If they attaches with long question, this question carries some 5 marks. The rest of the question will be carries some 15 marks, because the long question carries near 20 marks. So anyhow, this question is a very important question, right? just to go through this question. And remember, if you want to explain the transverse laws in stretched string, before that you have to remember the general expression for frequency of the vibrating string directly. If you remember the expression for frequency of the vibrating string, you can easily write all the 3 laws. Simply out of 4 values, every time we are writing the relationship between the 2 values, so that keeping the remaining 2 terms as constant. In the first law, relation between F and L, nu and L, keeping tension and linear mass density as constant. In the second law, relationship between the frequency and tension, keeping L and M are constant. In the third law, relationship between the frequency and linear mass density, keeping length and tension of the wire as constant. So, this is about all the 3 transverse laws in the stretched string. Let us do some problems based on this law, right. So, in the problem, let us do some problems which are related to this frequency. Problems are also very important, right. So, let us do one by one, and I think some of you are familiar with these expressions. This topic already have learnt at your intermediate level during that wave motion chapter. In the second year, as it is topic is there, some of you may be remember this topic, clear, right. In the problem they are asking like this: the fundamental frequency of vibrating stretched string of length 1 meter is 256 hertz. The fundamental frequency of the wire they have given as 256 hertz, and the length of the wire is given as some 1 meter. And the question is, find the frequency of the same string of half of the original length order identical conditions. When the length is exactly half of the original length, what is the original length? 1 meter. When the second length is half meter, definitely frequency of the wire will be affected. So, they are asking what is the frequency when the length of the string becomes half. Before that, we have to remember what is the relationship between the frequency and length of the wire. That is inversely proportional. Frequency is always inversely proportional to length of the wire. In other words, this is also can be written as nu 2 by nu 1 is equal to, this is inversely proportional. So, nu 2 by nu 1 is equal to L1 by L2. If they are in directly proportional, in such case we can write L2 by L1, but according to this relation, frequency and length are inversely proportional to each other. That is why if we are having 2 and 1 on LHS, we have to write as 1 and 2 on right hand side, clear. Just to substitute the values, you will get the answer. So, nu 2 by, what is the nu 1? That is the fundamental frequency 256, which equal to L1, original length is only 1 meter and it becomes half. This 2 goes in the numerator and multiplies with 1. So, nu 2 by 256 is equal to 2. Therefore, nu 2 is equal to 2 of 256 becomes 512 hertz. This is about the frequency of the wire. If the length of the wire is reduces to half of the original length. Let us do one more problem which is related to velocity of transverse wave in string. What is the expression for velocity of transverse wave? V is equal to under root of T by small m, clear, right. In the problem they are mentioning like this: a steel wire of the length 150 centimeter, the total length of the wire is given as 150 centimeter, okay, has a mass some 5 grams. The mass of the wire is given, total mass of the wire is given as some 5 grams and it is stretched with a tension 1200 Newton. The string is stretched between the two rigid supports which is equal to 1200 Newton. The question is, find the velocity of transverse wave traveling in the string. What is the velocity of the transverse wave in the string? Clear? This is about the problem, right? To do this problem, what we have to find out? V is equal to under root of T by small m. This is the required formula for the given problem, right? So, they are asking velocity of the transverse wave. For that, we need to find out tension and linear mass density. The tension of the wire is already given as 1200 Newton. So, next we have to find out linear mass density. How do we calculate? This is total mass of the wire. This is capital M, total mass of the wire. But they are asking, we have to find out linear mass density. How do we calculate linear mass density when we are having total mass and total length? Simply linear mass density, total mass by total length of the wire. Mass by length gives what? Linear mass density. But this is given in centimeter and this tension is given in Newton. So, we have to, and remember, while we are doing the problems, that too in physics problems, always the quantity should be in SI units, right? Standard international units. Centimeter is the CGS unit, we have to convert into meter. So, 150, 1 centimeter is equal to 1 by 100 meter or into 10 to the power of minus 2 meter. Simply I have converted centimeter into meter. Coming to grams, 1 gram is equal to 1 by 1000 kilograms or 10 to the power of minus 3 kilograms. So, finally, I have converted centimeter into meter, gram into kilogram. Substitute these values in this linear mass density. Capital M is 5 into 10 to the power of minus 3. Length of the wire 150 into 10 to the power of minus 2. Minus 2 gets cancelled, minus 1 will be there. So, this is 5 into 10 to the power of minus 1. This is 15 into 10 to the power of plus 1. 150 can be written as 15 into 10. So, 5 1 ja, 5 3 ja. So, finally, this value becomes, this 10 to the power of 1 goes into the numerator, multiplies with numerator, it becomes 10. Already here we are having 10 to the power of minus 1 becomes 10 to the power of minus 2 by 3. This is kilogram per meter. So, finally, I have calculated the value of small m as 10 to the power of minus 2 by 3 kilogram per meter. Just to substitute the small m and tension value in the required formula. V is equal to under root of, what is tension here? 1200. What is linear mass density? Just now only I have calculated, that is 1 by 3 into 10 to the power of minus 2. Clear? Right. So, this 3 goes into the numerator, multiplies the numerator. So, 12 3 is 36. Already here we are having 2 zeros. If I take 10 to the power of minus 2 from denominator to numerator, it becomes 10 to the power of plus 2 becomes 10 to the power of plus 4. Square root of 36 becomes 6. Square root of 10 to the power of 4 becomes 10 to the power of 2. So, finally, we get this is 6 into 10 to the power of 2 also can be written as 600 meter per second. This is the answer. Velocity of transverse wave in a stretched string. Let us do some more problems based on this formula in the next class. Until then, bye bye.